Okay. Worksheet 15. I meant to do this before I started. Sorry. When must superposition be used? When can superposition be avoided? We talked about that last week. Find the fault in the instructor-built circuit. Only exposed part of the circuit will be the wires to the nodes. Voltage measurements only. So we've got 1 to 0. You can measure 2 to 0, 3 to 0, and 4 to 0. So I'm actually going to have two voltage sources, a 7.5 to a 3, and then I'll have a couple parallel resistances, another parallel resistance, and another one. Another resistance in there. So you'll be able to make the measurements, and then you'll be able to tell me what I bugged. Okay? Tell me what I bugged. 4 through 7 is Millman's. Millman's is in Chapter 10 of the DC. Right here is Millman's theorem. Now, Millman's theorem assumes that you can put everything in parallel. So it's starting with this T-branch circuit here, and it's saying, can I redraw this so everything is in parallel? So battery 1 and R1, they can be parallel. R2's by itself, and then R3 is there. Now, Millman's interesting because he then takes all those parallels and he's going to come up with the voltage between the top and the bottom. Okay, the voltage between this point up here, this top line, and the voltage to the bottom line. That's what Millman's is doing. Now, this is one of those shortcuts that was made back before, you know, we had software that would do everything. And the voltage is going to be the current times the resistance. So he's really just using Ohm's law in a sense. So he takes the battery of each leg and divides by the resistance of each leg, and that a voltage divided by a resistance is really a current. So he's got a current for this one, a current for this one, and a current for this one. And he's dividing, he's adding those currents up, and he's dividing by 1 over the resistance. Well, if you remember the parallel formula, 1 over the resistance of 3 in parallel is really the reciprocal. Okay? So even though I'm dividing by the reciprocals of resistance, I'm really multiplying I times R, and that gives me a V. So if you go through it unit-wise, you see it. Okay, so that's the form. If you've got 3 branches like he's got up here, this is where you would start. Now, polarity is important. If one of these batteries had been upside down, there would be a negative number. You got to be consistent. If one direction's positive and you flip one of the other batteries, it has to be negative. Has to be. And the problem I give you, I think, is that way. The other thing to realize is if there is no battery in 2, the formula says the battery in 2, there is no battery in this line, so you put in a 0, or that term becomes 0. So it's the voltage divided by the resistance of each leg. And if there is no voltage, then the voltage is 0, so that term is 0. And then there's the voltage divided by the resistance of that third leg. And then 1 over resistance, 1 over resistance, 1 over resistance. Now you'd have to come up with a common denominator, and then you would have to flip it. and do the multiplication. And the answer for Millman's just comes out to be, you know, the voltage between the top and the bottom. Once you have that voltage between the top and the bottom, then you can take this 20 volts, let's say. Did he flip that? Oh, no, he didn't flip it. He's just doing his thing there. So once you have the voltage top and bottom, if I've got 28 volts and there's only 8 volts between the top and the bottom, then this resistor has to drop 20 volts. If I've got 8 volts top to bottom and this is 7, then this resistor actually drops a volt, or it actually adds a volt to it. So what he's trying to show you is the polarity is different. There's actually enough current flowing out of this battery here, this 28 volt battery, to actually force current into the 7 volt battery into its positive terminal. That's what he's trying to illustrate. And sometimes that happens, but you know the voltage drops, and if you know the voltage drops across the component, you know the current through. And I've said don't worry too much about the directions of currents. But that's Millman's. And then I give you a problem to work. -8 means you would turn that one upside down. Positive 12, that one is plus minus. And so I actually give you 4 legs, but only 2 of them have voltage sources. And so you're coming up with the value using Millman's theorem. Can you do it in SPICE? Yes, you can do this circuit in SPICE. So if you drew this out in a Millman's thing and then you drew it out in SPICE, you can check your answers with SPICE. You can check your answers that way. Once you get that voltage, then you know the voltage drop of the resistor in each leg, which the two that don't have voltage sources will be the voltage answer. And then you'll be able to come up with the currents. The voltage drops with the one, you have to figure out, okay, I'm going to this value and I've got 12 and I'm going to this value, so what's being dropped? So you sort of have to then go back and analyze it. But that's Millman's. For 8 through 10, I refer to a triangular shaped network, or a pi. Or delta network, containing R1, R2, and R3 is to be replaced by a T or a Y configuration. Now, I like to consider my networks as delta and Y. You sometimes will hear them referred to as pi and T. And it's just the way the resistors are arranged. That is also in this chapter. Delta is a triangle to Y. Y to delta is that. So it's down here at the bottom. So my delta network is 3 resistors that look like a triangle. My pi network is a variation of that. Notice that B, instead of coming to a point, they just made a box out of it. My Y network is 3 that look like a Y, and you can convert that into a T if you would like. Okay? So, delta Y, Y delta conversions. And he goes through how to do it if all your resistors are different. Okay? So if I'm converting from a Y to a delta, then my RA is this, my RB is that, my RC is this. Now what I don't like about his terminology is I think it's a little confusing, because he's using RA, RB, and RC on both. Well, I guess he's okay, because he's doing the 2, A to B. Alright, I'm okay with that. I use capital letters and smaller letters just to make it more obvious. So anyway, he works it out. If you've got a delta and you want to make it a Y, then this is what you do with the resistors. And you can work that out if you think about ohming. So if I ohm from A to B, in my Y network, I will get RA plus RB. That's the only path. If I ohm from A to B in my delta network, I've got this resistor in parallel with these two in series. So a lot of students, I tell them just ohm between A and B, and they say, oh, well, it's just this resistance. Well, no, it's not, because there's a secondary path. So it's this resistance in parallel with these two in series, and over here it's just these two in series. So if you take that into effect and you do all your ohming, A to B, A to C, C to B, and you boil down all that math, you get these conversions. Okay, where is this used? Oh, glad you asked. Remember our old friend the Wheatstone Bridge? Yes, yes. You can do it in Spice. Y'all have done it in Spice. But if you try to do this by figuring out what's in series and what's in parallel, you can't. So you can't reduce this to one resistor unless you go in and take this delta here and convert it to a Y. Now, once you do that conversion, then you can make this all one resistor, figure out how much current's flowing through, and then work back through and find all your values. And that's what he's doing here in his example. It's exactly what he's doing. Now, that's one of the questions I asked where they're not equal. Then I asked the question, well, what if they are all equal? I gotta get back to the worksheet. There we go. So here my resistances are all different. So I have to use those ugly formulas to figure out what it is. And it's a triangle network, R1 and 2 and 3. To be replaced by a T or a Y. So if you draw it out, you can sort of follow his terminology. So I'm using 1, 2, and 3, and A, B, and C. Okay. So R, A, B, and C is the Y, and 1, 2, and 3 is the delta, and those are just the resistors. That's how I like to do it. It's the same thing. Now, based on your calculations, if the pi or delta network contained 3 identical 6K resistors, what resistances would you need for the T or the Y? So if you go back in here and you look and say, okay, if RAB equals to RAC equals to RBC, what do I have? If all these values were equal, what would this reduce to? And let's say they were 6K. And make sure I've got the question right. If the pi or delta network contained 3 6K resistances, what resistances would the T or the Y network require? Okay. To convert a delta to a Y. So this is what we want, but all these are equal. And they're all equal to this. So these 3 terms are all the same. And if you put in a 6K, what do you get? What do you get? then you have the conversion. The easy conversion, the one you'll see most of the time. Because most of the time when you do a wide delta conversion, and most of the time when you're studying circuits, everything would be in symmetry. Alrighty. 13 is one that we've done earlier when we had our discussion about parallel resistances and what's the easy way. So here's your problem. I've got 3 resistors in parallel, 4K, 4K, and 2K. What's the equivalent? And then 14, 15, draw the Thevenin or Norton equivalent circuit to study a 5K in the following circuit. Now this one's going to take a little bit of work. So let's go back to I don't want to do that. It opened the second one. Alright, Thevenin. He likes using that circuit. Alright, so Thevenin, what you do is you determine your load. So you pick a resistor to study. So draw your circuit, pick your resistor to study. That's how I do it. So draw the Thevenin or the Norton equivalent circuit to study a 5K in the following circuit. So I've got a 14-volt supply, 2K in series, which then goes into 2 branches that have a 5K and a 3K, and the other branch has 2K. Oh, branch 2 has a 6K, so it's a lone 6K resistor. So 14 volts out of the positive side goes through a 2K, and then it splits into a branch that has a 5K and a 3K in series, and the other branch has a 6K. The branches then rejoin and return to minus power. So you study the load. And what we're trying to do is take this circuit here in his example and turn it into this circuit here. So what we got to do is we got to find the Thevenin voltage and we got to find the Thevenin resistance. Alright. So we take out the resistor we're going to study, and then we figure out what the voltage drop across that opening has to be. So that's the first step. Figure out which one you're going to study, which I gave you. Draw the circuit, take that out, and see what the voltage would be between those 2 points with that resistor removed. Once you have that, you have the Thevenin voltage. Okay? So he goes through calculating his example and he comes up with 11.2. And he says once you have the voltage between that gap, you have 11.2. You know your Thevenin voltage. Now you've got to find the resistance. Okay? So I went down too far. I did. Okay? So to find the resistance between these 2 points, you take the voltage sources, and these are 2 batteries, and you would short them out. And then you would say, okay, what ohms would I read between this point and this point across the open? So what you see in his circuit is I have a path through this 4 ohm, I have a path through the 1 ohm, both going to the other side. So essentially for his circuit, you've got a 1 ohm and a 4 ohm in parallel. And see, he redrew it without the battery, and he says that reduces to 0.8. Now once you put in your 0.8, your R Thevenin, you've got 11.2 volts and 0.8 ohms. And then you can put your load resistor or the resistor you're studying back in, and it will have the same current and the same voltage drop across it in this circuit as it did up here in the circuit that he started with, right here. And you can verify that in SPICE if you'd like. Alright, that's Thevenin. Now, Norton. Again, this is going to sound familiar. You're going to pick the resistor you want to study. And what you want to come up with is a Norton current and a Norton resistance. Okay? Now, when I remove the load that I'm going to study, I'm going to replace it with a wire. And then what I want to do is figure out how much current is flowing through that wire. If I can figure out how much current is flowing through that wire, that becomes my I Norton. So you see there's a wire there where that resistor used to be, and he figured out the current, and that current is my I Norton. Sometimes it's easier to calculate the current through a short than it is the voltage drop across an open. And so that's why I say you either do Thevenin or Norton. As you gain experience, as you do 10 or 12 of these problems, you would gain the experience you sort of would see. You can do either one. So sometimes it's easier to come up with a Thevenin voltage, sometimes it's easier to come up with a Norton current. What we've done with Thevenin and Norton so far is we have done the conversions. So we've been able to convert from a Thevenin to a Norton and from a Norton to a Thevenin. So if you can get one, you can get the other. That's easy. The nice part about this is the R Norton, as you have already figured out, hopefully, or remembered. The same process he did to find R Thevenin is the same process he does to find R Norton, and so the R Norton comes out to be exactly equal to R Thevenin. And when you convert, that's one of the things I listed, that they are equal. And so you can take any circuit basically and boil it down to a simplified circuit using Thevenin and Norton. Okay? So I want you to figure out the Norton or Thevenin and draw it. Draw the Thevenin or Norton equivalent circuit. Don't care which one. And that it comes back to minus power. And that is worksheet 15. How about that? And I got to remember to build that circuit and bring it. Or I could tell you what the voltage readings are. But it's more fun when you actually measure the voltages and then you figure out what's wrong. Because then it ties into what you see. And I thank you for watching.